Welcome to lecture number 8 on linear programming problem under this course on computational mathematics with C's Math. In this lecture, we will look at what is called revised simplex method. So if you look at the simplex method in a tabular form that we have looked at every stage, what are the computations which are involved? One involves all the columns corresponding to basic variables, that is called basic columns, and then we need, of course, the value on the right hand side that will result in the basic feasible solution, and then we require the bottom row, which is the reduced cost coefficient, and based on the reduced cost coefficient we decide incoming variable. So we need one column in order to decide incoming variable, and then we have to decide what is called outgoing variable. And if suppose xp is outgoing variable and xq is incoming variable, then we need to pivot the qth column. We need to pivot the qth column corresponding to the pth row. So that is what we do in simplex method. But in case so actually we require first m columns or any m columns which corresponds to basic columns. We require one last column corresponding to right hand side and one column corresponding to the incoming variable. So that's what we require. All the computations with respect to the remaining non-basic variables actually become redundant. If they do not enter into the basic variable, these computations become redundant. So if you compare, if you look at, for example, a linear programming problem involving large number of variables and the number of constraints are reasonably small, then lots of computations that we do in simplex method in the tabular form becomes redundant. So unnecessarily it is time consuming. So the revised simplex method takes care of that computation, right? So the revised simplex method actually reduces the amount of computation leading to an optimal solution by eliminating operations on the columns of A that do not enter the basic columns during this standard simplex method. Okay, we will see how we can implement this. Now let us look at little detail on how this we can do this revised simplex method. So again, let us assume that we are at a particular stage in simplex algorithm, and this A is given by B and AN. A has been split into B, AN, where B is matrix of the basic columns of A and AN is the matrix of non-basic columns of A. This we also saw in case of matrix form of simplex table. Right. Now what we need to do is we need to compute the inverse of this basic matrix, that is the matrix corresponding to basic variables. And we know that finding inverse of a matrix can be achieved by applying elementary row operation. So a sequence of elementary row operations will transform B into will find the inverse of B. And let us assume that the sequence of elementary row operations that are required in order to convert B into B inverse are given by E1, E2, dot, 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 Ek. What is E1, for example? E1 is going to be matrix obtained by applying appropriate elementary row operation on M cross M identity matrix. Here B is M by M matrix. So E1 is going to be M cross M matrix which is obtained by applying appropriate elementary row operation on identity matrix. And one can check that the inverse of elementary row matrices, elementary matrices are itself, and that is same as saying every elementary matrix is invertible. So therefore the B inverse is nothing but multiply ek times ek minus 1 dot 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 e2 times e1. That is the inverse of a matrix. So inverse of a matrix can be obtained by writing the multiplication of elementary matrices. Okay, now once we know the B inverse, then we know that the XB we can write as B inverse small b that solves the system of linear equations A XB is equal to B, right? And in this, so this will have m components. If we append 0, n minus m zeros coordinates, this is what is called basic feasible solution, right? So this basic feasible solution, the computation of basic feasible solution does not require computation of B inverse times AN, where what is AN? AN is matrix corresponding to non-basic variables, right? So and if you look at, if you compare this in this revised simplex method, as I said, we do not require B inverse AN. What we require is B inverse and the last column, which is B inverse B, and this is nothing but m cross m plus 1 matrix. This is m by m matrix, this is one column, this is therefore this is m cross m plus 1 matrix, which is much smaller compared to the original size, which is m cross n plus 1 matrix. So therefore in the revised simplex method we are taking care of matrix which is much more smaller than the simplex method, right? Now let us look at what we are going to do. The next step when we are going to decide incoming column and outgoing variables, incoming variables and outgoing variables. So suppose when you have applied this or you have updated this simplex method, you have got this column size y1 from a1a to an, and the last column is, let us say, b. You have got columns y1, y2 dot 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 yn, and the last column is y0. This is what we wrote in the theory of simplex method, and in fact the first m columns of this will constitute identity matrix. So y1, y2, ym will be identity, and the remaining are going to be ym plus 1 up to yn. So and suppose we have chosen AQ column to enter the basic. Now if AQ column enters the basic, then YQ is going to be B inverse AQ, right? B inverse times AQ will give me the YQ column after updating this simplex table, right? And the last column is going to be Y0, which is going to be B inverse B. So this we already know, we have already looked at this in the simplex method. Now let us assume, so once we have decided AQ, which is going to be entering variable, then we have to now decide what is outgoing variable. And to decide entering variable AQ, we have to look at the reduced cost coefficient and one which is the most negative in case there are, right? And then how do we find this index? So we next, in order to decide outgoing variable, we have to look at the ratio of the right hand side by the entries in the incoming column corresponding to only those entries which are positive. This again we have seen that, and look at the index at which this minimum occurs, right? So suppose the P is the minimum, the argument at which this minimum occurs, then the PQ entry is going to be pivot entry. So we have to pivot the last column, that is YQ. Now what we are going to do, so we will look at another column YQ. So in this B inverse Y0, we will append another column YQ. So now this matrix is of size m cross m plus 2. Still it will be much smaller than m cross n plus 1, right? So once we have looked at this B inverse Y0 YQ, now we will pivot this about pth element in the last column. So this entry, what is this entry in this column? It is going to be y1q, y2q dot 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 somewhere ypq and dot 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 ymq. So ypq is going to be the pivot entry, pivot element, so that we have to pivot. Okay, so now when we pivot that, then we are going to revise this matrix or the simplex table in case of we are making use of simplex table. Now when you pivot this, what is that you are going to require? This PQ entry you have to make it 1, and the remaining entry in all that column you have to make it 0. So that means that pth row you need to divide by ypq so that it will become 1, and the remaining entries you have to, so therefore once you have divided the pth row by ypq is non-zero, then this becomes 1, and therefore the first row, if you want to make it 0, you have to multiply the pth row by y1q, negative of that, and then add to first row. So that is, and this will correspond to the sequence of elementary row operation, which is, let us say, denoted by this matrix ek. So when you multiply ek by yq, what you are going to get? You are going to get all the entries will become 0 except the pth entry, which is 1. This is unit vector whose pth coordinate is 1, remaining are all 0. So this is what you will get, ek plus 1 times yq. This is equal to ep. Right. So that is how you are going to pivot. Now if you look at the same operation, you have to apply to B inverse, and it actually results in this simplex table. Now this simplex table will be updated, and what you are going to get, this will go into the first B inverse will become ek plus 1 B inverse, and then this y naught will become now ek plus 1 y naught, and this yq we saw it is ep. Right. So if I call this new basis matrix as B new, then B new inverse, since B is invertible and ek plus 1 inverse is itself, this is going to be ek plus 1 times B inverse. This is not AB inverse, this is B inverse. So let me write this as B inverse. That is what you are going to get. That is nothing but ek plus 1 into ek plus dot 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 e1. So that is what you are going to get. So what it also means is that once you know the B inverse at any stage in the simplex table, the next updated the basic matrix inverse, if you want to compute, all you need to do is multiply by this elementary matrix ek plus 1, and which ek plus 1 is coming from the pivoting this last column. So it is easier to compute this rather than compute the inverse of entire this M cross M matrix. So that is the advantage. One, finding B inverse becomes easy. Next, now in this case you can see here that we have not taken into account column M plus 1, M plus 2 dot dot dot, let us say q minus 1 and then q plus 1 up to n. So out of n minus m non-basic columns, only one of them are taken into consideration, that is qth column, and the one is the last column. So therefore, in case for example, if you have 100 columns, 100 variables and 50 rows, that means you are dealing with matrix 52 cross let us say 50 cross 52 rather than 50 cross 100. So that size reduces. So that is why this is called reduced revised simplex method. This method is called revised simplex method. Okay, now let us look at what will be the algorithm to solve this problem. So we will call this as a revised simplex algorithm. So the first step in this is to form the revised simplex table corresponding to initial basic feasible solution, right? So this once you have guessed what is initial basic feasible solution, which most often corresponds to the columns corresponding to slack variables in case of standard linear programming problem. So then you write down B inverse and B inverse B. B inverse B is your y naught. That is the first step. Then calculate this reduced cost coefficient using this formula. R transpose is Cn transpose minus Cb transpose B inverse An. That is the reduced cost coefficient. And just also keep track of the indices of this reduced cost coefficient. And then in case all the entries of this R transpose are non-negative, you have reached the optimal solution. Otherwise you have to go to the next step, that is choose reduced cost coefficient which is most negative, and look at the column corresponding to that, which is YQ. And what is YQ? YQ is obtained by B inverse times the qth column of A. That is your YQ. Once you have found out YQ, now look at, once you have the column YQ, one column YQ, and then the right hand side column, that is Y0, look at the ratio yi0 upon yiq for yiq positive, and look at the index at which this minimum occurs. Again, in case that none of this yiq is positive, then we know that this problem is unbounded. Right? Now what you have to do, once you have decided P, then you form the augmented revised simplex table B inverse Y0 and AQ, and pivot the pth entry of the last column, and form the updated revised simplex table by taking first m+1 columns of the resulting augmented revised simplex table. So, and we know that when we do this pivoting of the pth element in the last column, this amounts to multiplying by this matrix ek plus 1, where ek plus 1 is given by this. Once we have this, then we got the new, not only we get the new basic columns, but we get new basic matrix B, but we also get B inverse, inverse of this new basic matrix, which is again ek plus 1 times B inverse. Right. So this is what is called revised simplex table, and this revised simplex table reduces the computation time. Okay. So you are saving a lot of time which are consumed in order to apply pivoting to non-basic columns in the simplex method, which do not enter into the basic variable. Okay. Next, let us look at how we can solve this using the Sage math. How we can apply, or how we can make use of revised simplex method in order to solve a linear programming problem. So there is an inbuilt function which we will be using. We will not, we are not going to write this each and every step, but we will rather use inbuilt function. So let us start with a problem. So this is a problem. Maximize 3x1 plus x2 plus 3x3 subject to 2x1 plus x2 plus x3 less than equal to 2, x1 plus 2x2 plus 3x3 less than equal to 5, and 2x1 plus 2x2 plus x3 less than equal to 6. All xi's are non-negative. So what the first step is to write this coefficient matrix A, the right hand side B, and the coefficient of this objective function in standard form. So first we are going to convert this into standard form. So that will be minimization type. Therefore, the coefficient of the C, the coefficient of the C is going to be negative of 3, negative 1, negative 3. Right. So this we have seen earlier. So this is how we define the problem in standard form. This problem is minimization type. All the design variables are non-negative, and the variables are x1, x2, x3. So now let us look at what is this matrix, what is this problem P. So let me ask it to show what is P. That's the problem. It is though we wrote it here minimization type, but then says looks at the problem, maximization problem in standard form with all less than equal to sign. Right. So that's the problem. Okay. Now in this P, once you have converted this P into standard form, there are various methods that you can apply. One of the method is called P dot revised dictionary. So when you apply this, the matrix A, which we have split it into into B and AN, all those things you can see. So now let us convert this into revised dictionary, and then ask it to show what is the basic matrix, and then similarly what is the non-basic matrix corresponding to non-basic variables. So this is A dot B and A dot AN will print all these things, and that is what you can see here. So when you have converted this to a standard form, you have introduced the slack variables x4, x5, x6, and that corresponds to basic variables. So the matrix B is going to be identity, and the AN, which the Sage represents as D here, it represents as D. Let me write here AN this an, this is going to be the first column of A, second column of A, third column of A with respect to x1, x2, x3, right? And you can also write down what is the simplex step. So if I ask you to show what is D is revised dictionary, then this is what is the D. D gives you the basic variables, the coefficient of the C with respect to basic variables, B inverse, it also gives you Y, and in this case Y actually is, I'll just tell you what is Y here. If you look at this reduced cost coefficient, where is it? This is here. If you look at this reduced cost coefficient, then this CB transpose B inverse is denoted by Y in this Sage math. So this, therefore RT is going to be Cn transpose minus Y, this will be represented by Y transpose An. So that is your Y here, right? So this Y transpose An is calculated, therefore Cn transpose minus Y transpose An, this is the R transpose, which is the reduced cost coefficient, is written here. So all these things it reports, and including the B inverse B, Y column, that is to calculate reduced cost coefficient. Right. Once we know all these things, now let us look at this stage whether this problem, what are the basic, you can also find out what are the basic and non-basic variables. So D dot basic variables give me x4, x5, x6, which are the basic variables. Non-basic variables are x1, x2, x3, right? Next, let us look at what is the coefficient of the basic coefficient of the objective function corresponding to basic and non-basic variables. So that is D dot CB and D dot CN. So here the coefficient with respect to basic variables, the value of C are 0, and with respect to non-basic variables are 3, 1, 3, right? So you can also find out what are the constant term, which is the right hand side. D dot constant terms are going to be the right hand side, and you can see here the right hand side is B inverse B, but B is identity, so it will be just the right hand side of Ax equal to B, that is B, 2, 5, 6, right? Once you have all these things, then you can check whether at this stage whether D is feasible, right? So it says that this particular value which represents x4 is equal to 2, x5 is equal to 5, and x6 is equal to 6, this is a feasible solution. So this is a feasible. Now once it is a feasible, then you can find out what is the value of the objective function. We know that it is going to be 0 because none of the x1, x2, x3 has entered into the basic variable, so the objective function value is going to be 0, right? So that is and it is feasible but not optimal. You can just find out whether this is an optimal. The answer is no, this is not an optimal solution, though it is basic feasible, but it is not optimal. Therefore we need to revise the dictionary. That is same as saying we have to go to the next step. That means we need to find out incoming variable and outgoing variables. So to do that, of course you can find out what are the objective function coefficients that we have looked at. You can find out what are the possible simplex method steps, right? So the simplex method steps, in this case you can see here we are dealing with maximization problem, and the reduced cost coefficient are all positive. So for this, in order to get the optimal solution, all the reduced cost coefficients should be negative actually, right? In case of minimization problem, it should become non-negative, but in case of maximization problem, all the reduced cost coefficients should become negative in order to get optimal value. Since here all are positive, so you have to the solution is not optimal, therefore you have to choose one which is most positive. So therefore, and this is corresponding to x1, this is corresponding to x2, this is corresponding to x3 non-basic, right? So now let us look at what are the possible simplex steps. So it says that you can have x1, you can have x2, you can have x3. So one of these are going to be the possible steps that are going to entering variable. So let us look at, we can in principle we can enter any one of these, but let us choose x1 to enter. if I say x1 is entering variable, d dot enter is equal to 1, this is same as saying manually you are saying says that you take x1 as entering variable. Once you have decided the entering variable, then it will also give you the ratio. And if you just go back, this x1 coefficients in this are going to be 2, 1, 2, and the ratio here these are 2, 5, 6. So you have to find out the ratio. So 2 by 2, 1, 5 by 1, 1, 6 by 2 is 3. So these are the ratio. So it can report what are the ratios, and that is what you can see here. With respect to x1 basic variable, the ratio is 1. With respect to x5, the basic variable, the ratio is 5. With respect to x6, the ratio is 3. Therefore, the minimum is 1. So we will take leaving variable with respect to minimum, which corresponds to x4. So let us take x4 as leaving variable. So d dot leave is equal to x4. Once you have decided or once you have given what is entering variable and what is leaving variable, now you update the dictionary D. Now once you have updated the dictionary D, then ask it to show what is D. Again it will give you the updated dictionary. Now you can see here the B has changed, therefore B inverse has changed, and corresponding Y and B inverse B, that has also changed. Now since x1 entered, x4 went out, so x4 becomes now non-basic variable, and x2 and x3 are also non-basic, and basic variables are x1, x5, x6. This is the coefficient with respect to the basic variables, and this is your y transpose an. This is the reduced cost coefficient. Again you can see here there is one positive entry, therefore this solution is not optimal. But again you can check whether this is optimal. So or you can find out what is the matrix corresponding to the basic variable. That is, since x1 has entered, the first column will enter, and then non-basic, this is the matrix corresponding to the non-basic variable, and this is the revised simplex step that we already have. And as I said, this is positive, the reduced cost coefficient is positive, therefore we have not reached optimal. Therefore now again we have to decide which is incoming and outgoing. So in this case, we can say the x3 is incoming, there is only one positive. So we will say, we can of course find out possible simplex method steps. In this case there is only one, namely x3. So x3 is incoming. So we will say d dot enter x3. So x3 is entering variable, and then we will decide what are the ratios. Ratios, there are only two positive things in this column. Look at the corresponding to x3, there are only two positive things this here. So therefore the ratio in this case is 2 and 5 by 8, 8 by 5, not 5 by 8. Therefore the minimum is going to be this. So therefore let us of course you can find out what are the constant terms. Let us, and you can find out what is the an, what is the ratio that we have already looked at. So once we have looked at the ratio, then we can ask which one will be leaving. So this is the smallest ratio, so we'll say leave x5. Now what will happen? Now in this case x5 has left, and which one has entered? x3 has entered. So therefore next we need to do is we can find out what is the leaving variable. It says it's 5, and then we again update D. And once you have updated D, then ask it to show this revised dictionary. And in this case you can see here all the reduced cost coefficient has become negative. Therefore this particular is an optimal solution, and the value of the objective function we have to calculate. And in this case the solution is x1 is equal to 1 by 5, x2 is equal to 0 because it is non-basic variable, x3 is 8 by 5. And let us find out what is the value of the objective function at this stage. So d dot optimal, is it optimal? The answer is true. So what we have got is an optimal solution, and the value of the objective function at this is 27 by 5. So this problem has solution. The optimal value or minimum value for this is 27 by 5, and it occurs at x1 is equal to 1 by 5 and x3 is equal to 8 by 5. Right. So that's how you can solve. Of course, you can check what is the solution. So d dot basic solution will give you x1 is equal to 1 by 5, 0, x3 is equal to 8 by 5. That is how you solve step by step using this inbuilt Sage function. So remember what is the main step here. Once you have defined this P, that is the problem, using interactive LP problem which we have used earlier. After that you convert into standard form and then look at the revised dictionary, and after that once you have revised dictionary, then you can find out what are the possible steps. Next step, in case it is not an optimal, once you have decided what are the possible steps, then you enter the variable which is going to enter, d dot enter, find out the ratio, choose the one which is the minimum, then say what is the leaving variable, and then update the dictionary. Once you have updated dictionary, again check whether the revised cost coefficients are all negative. In case it is negative, you have reached optimal. Otherwise, you again find out what are the possible steps, give the entering variable, give the leaving variable, and then update the simplex table. Keep on doing till all the reduced cost coefficient becomes negative in case of maximization problem, because that is what Sage will consider. The standard problem that Sage considers for solving is maximization type, right? So let us look at how we can solve this problem using inbuilt Sage function. So here we have done step by step revised simplex method. Now let us look at the same problem. We again we define this, and then once you have said that you make this in standard form, there is an inbuilt function called run_revise simplex method. So this will run all the steps of revise simplex method. So let me execute this. Once you execute this, you can see here this is the first step, right? This is the identity matrix, and the red one tells you that this is the outgoing variable. This is going to be outgoing variable, and here the green one tells you what is the incoming variable. So x1 enters, x4 goes out. That is what it says here. Similarly, the next step is and again you can see here it computes B inverse using E inverse and the B old, right? And E inverse is going to be this one, which is the column which is going to enter. So that's exactly what you see here. So in principle, you do not require to compute inverse all over again, but rather it is just you multiply this matrix, the old matrix, by this elementary matrix, right? So this once we have done this is the next step, revised simplex table, and in this case again it is computing the right hand side, it is computing the B inverse of the entering variable, which were in this case x4. So in this case now it computes the ratio also. The minimum ratio is this, therefore this is outgoing variable and this is incoming variable, therefore x3 enters and x5 leaves, and it does one more step, and then after that it finds the value, value of the objective function. In this case for the maximum is -27/5 because the problem was minimization type, and the optimal solution occurs at 1/5, 8/5. Okay, so that's how you can either run revise simplex method, or you can do step by step. Step by step will give you a little more. I mean, you will once you understand this method, you can do step by step, or you can run this itself, right? Okay, so let us in case as I said in the last class, in case this p dot run revise simplex method is not able to display everything properly, which can happen in some system, in that case you can try to run this particular code and it will display all the steps. So this is more likely to display all the steps, right? This is same as the previous one, but as I said, in some system I found that the p dot revise simplex method will not be able to display everything properly. In that case you can show this, right? Okay, now you can also solve the same problem using mixed integer linear programming problem, and we have already explained this, so I'm not going to get into this in more detail. So you define the problem, define the variables, then you set the objective function, add all the constraints and ask it to show what is the problem, and then ask it to solve. When you solve this, it will give you the objective function value. So you can see here 27 by 5 is 5.4, and this occurs at x1 is equal to 0.2 and x2 is equal to 0, x3 is equal to 1 by 1.6. Right. So let us look at one more problem just to kind of consolidate what we are doing. So this is a problem in 4 variables. Maximize this subjected to these less than equal to constraints. So again, what we are going to do, we will define the matrix A, the right hand side B, and the coefficients of the objective function in C. Once we have done this, then we will create the problem using interactive LP problem by giving A, B, C, naming the variables x1, x2, x3, x4. All the variable types are non-negative. The problem is of maximization type, and then convert this into standard form and then ask it to show this problem. Right. Once you have done this, now what we need to do, we can find the revised dictionary. Right. That will be giving you the starting basic matrix and the non-basic matrix and the basic initial revised simplex steps. So again, you can see here this revised reduced cost coefficient are 3, 4, 1, 7. So all of them are positive in fact. So we choose one which is the most positive, and first check whether D is feasible. The answer is yes. Check whether this is optimal. The answer is no. And then find out what are the possible steps. So here x1, x2, x3, x4, anyone can enter. This is x1, x2, x3, x4, anyone can enter. So you choose one. We can choose the one which is the most positive, in this case x4. So we will say enter x4 and then compute the ratios, right? The ratio are going to be 7, 3 by 5 and 4. So this the smallest is 3 by 5, that means x6 will leave. So we'll say that d dot leave is equal is x6. Once you have decided entering and leaving variable, then you update d. Once you have updated d, ask it to show what is d. Once you ask it to show d, it will give you the steps. Again, you can see here the reduced cost coefficient, there is one positive still. So therefore x1 will be now entering variable, and then you find out the entering variable. So you call x1 as entering variable, find out what are the ratios, and once you have found out the ratios, you can see here this is 1.5, this is 34, this is the minimum. So x5 will enter. So ask x5 to leave, and once you have done this, update d, the dictionary, and ask it to show what is d. Then you can see here now all are now negative. Therefore we have reached the optimal solution. All the reduced cost coefficients are negative. Therefore we have reached the optimal solution, and you can find out what is the optimal value of d. It says it is true. What are the values at this optimal? This is 16 by 19, 0, 0, 5 by 19. So x1 is equal to this, x2 is equal to 0, x3 is 0, x4 is equal to 5 by 19, and the value of the objective function at this stage is 83 by 19, which is the solution. Right? And again you can run this run revise simplex method. So it will show all the steps together. So you can see here, these are the steps. It tells you what is the leaving variable, what is the entering variable, updates the basic and non-basic columns. Once you have done this, then again it is taking the one which is negative, positive. This is x2, so x2 enters, x6 leaves, that is coming from the ratio. Once you have this, then you can update again the new b, and this after this again there is one positive. In this case this one is positive, so x4 leaves, and here x2 enters. Then once you have updated, you get the solution. That is what we got when we did each step separately. right? Or you can run this code in case Sage is not able to display p dot run revise simplex method, right? So this is how you can apply revise simplex method to any problem. And what is the advantage of revise simplex method? It reduces the number of steps, especially it does not do any computation with respect to non-basic columns which do not enter into the basic variables, right? Let me leave you with some exercises. So these are a few exercises you can try to solve. Maximize this problem, and then second problem is again of maximization type. This is the third problem, and this is the fourth problem, and 4.1 and 4.2. So these are the most of these problems are standard problems. So try to run create the problem using interactive LP problem, and then create in the standard form. Then you create revise dictionary, and once you have created revise dictionary, I expect all of you to do step by step. That means at every stage you decide what is the entering variable, what is the leaving variable, and also run the entire thing. Okay, and verify your results using mixed integer linear program also. Okay, so these are the problems. So let me stop here, and in the next class we will look at, in all the problems that we have solved so far, we had initial basic feasible solutions readily available. But what if you are unable to guess initial basic feasible solution? Okay, in that case you cannot start simplex method or revise simplex method. So you need to find using some systematic way of starting simplex table. That is basic feasible solution you have to find to begin in order to start the simplex method. So we will be looking at two methods. One is called two-phase simplex method, and another is called big M method, in order to take care of starting basic feasible solution. Thank you very much.